Thank you for the kind introduction. We are developing a concurrent multi-scale model to study the fracturing glassy polymer systems. Before jumping to the method and the simulations, I will have a brief introduction. Why we need to do the coupling between the continuum domain and the particle domain, which we are doing here. As we know, the linear elastic fracture mechanics is limited to the very small deformations and linear material behaviors. For the soft materials in polymers, the theory fails because in the front of the crack tip, we have a very nonlinear large deformation and viscoelastic process. Developing new theories also is challenging because of the material complexity, sometimes like the anisotropy, adding the nanoparticles and so on makes it very complicated. There is a limitation by experimental methods also because this fracture has a multi-scale nature and it starts at a very, very small scale where the molecular failure happens and the bond breakage happens in the very, very small scales. So we need the optical devices to see what is happening at the crack tip, at the nanoscale. And most of the times, this optical device has a limited resolution and we need a complicated experimental setup. On the other hand, the molecular dynamic simulation is a very powerful tool to see for example, the polymer chains interaction at the crack tip, how the bond breaking happenings and so on. But the thing is that the MD simulation is limited to very, very small times scale, like femtosecond, or very small length scale also, like a nanosecond. We can simulate like a polymer system with MD simulation, like in the order of 100 nanonewton. And also we cannot simulate very large polymer chains because the system will not relax. Here we have a PLA, polymer with 30 monomer, which is coarse-grained to the, each atom, all atom model coarse-grained to the single bit. So another problem with pure MD simulation is that we have to use periodic boundary condition to do this kind of simulations. And when we have to apply these deformations through the periodic boundary condition to the material, which this kind of test is completely different than the standard fracture test in the lab we have in the lab. So what we are doing, we are developing a hybrid continuum to particle method for the amorphous polymer system. Before, for the crystal material, this kind of methods have been developed, but not for the amorphous polymers. This method also is called like partition-based method because we have like different partition for different resolution. For example, here, the green part is the particle domain where the polymer chains are located. The red part is the continuum domain, which we are using the finite element to analyze this model, this domain. We have like the crack tip here, and we have this bridging domain, the blue part, which is called bridging domain. This is the domain where this green part, the MD particles and the continuum domain overlaps here. And the couplings, the kinematic coupling between these two domains happens here. So to enforce this kind of coupling, we have this auxiliary point, this gray point. It's called anchor points. These points are connected to the polymer chain using this red spring, these harmonic springs to anchor the polymer. So when we are doing the simulations, first we run the simulation for the particle domain. The anchor points and the FE part is frozen during the simulation for the particle domain. We collect the forces on the anchor point. After the MD simulation, we transfer these forces to the finite element nodes. We do the FE analysis. We have the deformation for the elements. And then we calculate the new position for the anchor point. And for the next MD run, we update the position of the anchor points in our simulation. So these anchor points, like the red points here, are in both sides, on the MD side, the particle side, on the FE side. Ideally, these two anchor points should coincide, To enforce this coupling, we introduced this KC, this blue spring, which enforces this coupling between these two domains, glues the particle domain to the finite element domain. This KC appears as a penalty term in the energy equation of the finite element domain. So this is the final equation which we have. N is the shape function, U is the nodal displacement, and FAAP is the forces calculated from the particle domain. So every time we run the molecular dynamics simulation, and we solve these equations for the FE part. So before doing any fracture test, it's very important to test if the results for the model is correct or not, for the coupled system is correct or not. Here, this particle domain is embedded in the continuum domain, in the FEM domain. And we do a tensile tension test and compare the result with the pure finite element. Here we have like 1% strain for the pure FE, linear elastic, the blue line. And we do this deformation for the coupled system in 10 load steps, each time 0.1% strain, like here. We do the deformation on this surface and this surface. We fix the deformation after the load step. We do MD-FE iteration. Here we did like 70 times and 50 times FE MD iteration. And then we apply the next load step on after the simulation converges to the pure FE or reference system. So for the fracture, which we are doing, is still developing the method. The purple part here is the polymer chains located here. This green part is the bridging domain, where the continuum domain and particle domain overlaps. These red points are the anchor points, which enforce the coupling between these two domains. And here we have the crack tip. This is a very small system so far. We are working on it. It's like 20 nanometer. The system size is very small. So we do the deformation each load step, 0.1% on this surface and this surface. It's a 3D model. And we do 50 iteration, MD-FE iteration per load step. So for the particle domain, we don't need to develop any constitutive model, just we do for the fracture, for the continuum fracture theories. And we just need to define the potential energy between the atoms, the particles, and the fracture will be happen. And we can see like fracture propagation through the polymer chains. So what we are doing right now we are trying to see like what is happening at the crack tip here in the polymer system. This is the PLA, and how these polymer chains, which I colored some of them here with red, blue, and orange, how these polymer chains behave at the crack tip, close to the crack tip, and away from the crack tip. The work still is under development. This is how the polymers move in front of the crack tip. So we are trying to see if the fracture is dominated by the bond breaking in the polymer chain, or the polymer chain clot process is happening here. So in the future, also, we will look at the nanoparticles, how the nanoparticles affects the fracture propagation. And we will use this multi-scale method also to look at the self-healing after the fracture happens, how the self-healing happens in the polymer system. Thank you for the attention.